Hello and welcome! In today's video, I'm going to be covering how to solve an elastic collision. This is a totally elastic collision that's covered in introductory physics courses. While I read this, I'm going to kind of draw what's happening on the screen to help us visualize the problem. So, two balls of the same mass are set on a table and put on a collision course. So we have some kind of table. Using a protractor, the one ball starts rolling at a 25-degree angle measured above one edge of the table at 0.5 meters per second. So that means we have a ball down here, and it's rolling 25 degrees above the horizontal at 0.5 meters per second. Alright. The other ball is made to roll perpendicular to the opposite edge of the table. Now that's a bit wordy, but basically, the other ball is going straight down, perpendicular to the opposite edge, at 0.75 meters per second. After colliding, the first ball's new velocity is measured to be 0.45 meters per second, and the second ball is now rolling parallel to the edge of the table that it was launched from. So that means use a lighter color to kind of symbolize the blue. Hi, Editing Lauren here. I just want to let you know that 0.45 meters per second? I misread that and wrote down 0.75 meters per second, and then in my math I used 0.7. So don't get confused later on when 0.7 shows up. I just wanted to let you know, alright, enjoy. It's now going off in some direction. We don't know which direction, but we know that it's going 0.45 meters per second. And then our second one, I don't have another green. Alright, this one's gonna be pink. This one is now going this way at an unknown velocity. So I'm gonna make this one, I'm just gonna point it in this direction. I have no idea if that's the way it's actually gonna go. And this is at 0.75 meters per second, and this is an unknown theta. Because this is an elastic collision, there are a few formulas we can use to solve this. The first of which is the sum of the initial momentums equals the sum of the final momentums. Or more easily remembered, initial masses times the initial velocities equals the sum of the final masses times the final velocities. Now, our masses have not changed in this particular problem, but this formula is kind of the general approach. It's the one that's, you can modify it as you wish. And this differs from an inelastic collision because our final side of our equation, or our equal sign, is still a summation. Our objects have not become one object. They're still two distinct things. And another little tidbit that you want to kind of keep in the back of your head whenever you solve these kind of problems, this formula only works in one direction at a time. So, I'll do this. This one's a little cleaner, like this. Where this is y and this is x. We have a coordinate plane, and our objects are moving in velocities that are not strictly in one direction. So whenever we use this equation up here, we have to use components. So this becomes the sum of our masses times our initial velocities in the x direction equals the sum of our masses times the final velocities in the x direction, and the sum of our masses times the initial velocity in the y direction equals the sum of our masses times the velocity finally in the y direction. And from here, now that we have these sorted out, we can actually start solving the problem. If we end up needing it, there's a third formula that we can use. I'll write it down in case you're curious about it, but there's not a guarantee you're always going to use it. It's basically the sum of the kinetic energy initially equals the sum of the kinetic energy finally, where the kinetic energy is 1/2 mv squared. You can use this formula if you're dealing with an elastic collision, but you don't use them in every single elastic collision problem. usually these are plenty sufficient. Okay, and now that we've kind of covered the setup, we're actually going to do some math. I'm going to start with breaking these things into components. So ball 1, and then ball 2. And this whole like bookkeeping method that I'm doing here, it's my personal preference. You don't have to do it whenever you solve one of these problems if you feel as though you don't need it. So Vix, this is the initial velocity in the x direction. That would be this component, because there are 2 components here. The blue highlighted is the y component, the green highlighted is the x component. If you have some questions or you're a little confused on how to find components, I have 3 videos that are about vector math, addition and subtraction and all of that fun stuff. They kind of go over how to find components, if you want a more in-depth explanation of what a component is. The x component for our first ball initially is 0.5 times the cosine of 25 degrees. And that I got from SOHCAHTOA, where the side of the right triangle that we're trying to find is adjacent to the known angle, so I used cosine, times the hypotenuse, which is 0.5. Our initial velocity in the y direction is 0.5 times the sine of 25 degrees for the same similar logic. The side that we're looking for is opposite to the known angle, so we use sine. Now, Vfx and Vfy are a little different. We know the magnitude, but we don't know the sign. So I'm going to kind of approach this similarly, where the x direction is still the cosine of an unknown theta, and this is the sine of an unknown theta. And those are all of the components of the velocities for our first ball. The second one, we approach identically. We just have different numbers that we care about. So initially, the second ball is going only in the y direction, which means there is no initial velocity in the x direction. And there is a 0.75 meter per second velocity in the y direction. And it's negative because it's going down. In the x direction, or the final velocity in the x direction, is an unknown velocity, but we know that it's positive because we've pointed it to the right. And I just kind of arbitrarily assigned these angles here. Like this one, the second ball could be going to the left, and all of that fun stuff. That'll work out in our math. And there is no velocity in the y direction finally because our second ball is parallel to the x-axis. Okay, and now that we've kind of figured out all of that fun stuff, we can start using these 2 formulas. And as a rule of thumb, I like to start with the x direction first, just because I honestly could not give you a concrete explanation. I just like the x direction more. So I like to do it first. If you want to do the y direction first, you definitely can. All right, so this is our formula, and I'm going to start plugging in what we know. We have an unknown mass times our initial velocity in the x direction for the first ball, because we're doing a summation. So I'm going to start with the first ball plus the mass times velocity of the second ball. An unknown mass times the x direction initial velocity, which is 0.5. I'm going to color code this. Times 0.5 times the cosine of 25 degrees plus another mass, but they are the same mass, so I'm going to use the same letter, times 0. And this equals, slide this way, m times 0.7 times the cosine of theta plus m times v. Oops, that should be green. Times v. And I've just pulled these numbers from my little table up here. All of our masses cancel out in this particular problem because they're the same magnitude. The balls have the same mass, so I can cross out the masses in this problem. And from here, we can see that I have two unknowns. I have a theta and an unknown v. That's totally fine. We can rewrite this to equal one of those things if we are so inclined. We can clean it up a little bit and then see where our heart takes us, or we can use our second formula. I'm going to clean this up a smidgen and then we're going to go to the y. So this becomes 0.5 times the cosine of 25 degrees. And if I were to consult my calculator, this is a gross number. 0.4532. And this equals, that's the wrong color. This equals 0.7 cosine of theta plus v. And we've hit a bit of a dead end, so now I'm going to go to the y direction. This is not a problem that we've hit a dead end. In fact, it's a good thing that we have two unknowns, because we have two unknowns and two formulas, which means we can use substitution pretty easily. So if I were to write this out to kind of give us a gauge of what we're doing, I'm going to just redo this whole summation using the y direction numbers. And I'm not going to bother writing the m's because they're going to cancel just like last time. So this is the initial velocity in the y direction for the first ball is 0.5 times the sine of 25 degrees plus the initial velocity in the y direction for the second ball, which is negative 0.75. And this equals the velocity in the y direction for the first ball finally, which is a 0.7 times the sine of theta. As you can kind of see, I'm writing them down here. And then this is plus the final velocity for the second ball in the y direction, which is 0. All right. Now, I did notice one thing that I forgot to kind of touch on before. So let me slide up here and we'll do that real quick. Just like before, we have two components. Our x component's going this way for our final velocity of our first ball. And our y component is going up here like this. Our x component is pointed in the negative x direction, so over here, this is a negative 0.7. So this is going to be negative, and this is going to be negative there. All right, and now that we've kind of covered that and I've corrected that, we're going to jump back to our summation of our momentums. Our y direction only has one variable, which is phenomenal. That's very handy. We can solve this algebraically for that variable. So 0.5 times the sine of 25 degrees minus 0.75 is a negative 0.5. I'm going to use red. Negative 0.5387 equals a positive 0.7 times the sine of theta. Now, next thing I'm going to do is I'm going to divide this whole thing by 0.7. All right, and then this becomes negative 0.7696. Oops. Good thing I read that because I definitely wrote that wrong. 96 equals the sine of theta. Cool. So now I can just sine inverse this, and we get the sine inverse of negative 0.7696 equals theta. So theta equals negative 50.314 degrees. And I've gone off screen. There you go. This is our theta. And the fact that we have a negative number means nothing. It just means that this theta, our ball is actually going underneath the horizontal this way. I'm going to use the same color. It's going like this, and this is 50 degrees. That's all that means. And we can correct this in our math if we wanted to, but for the sake of our math, I'm going to continue using this negative 50 degrees. And that is because all of the signs that we've assigned to our components here was under the assumption our velocity was pointed upwards. So if I were to use a positive 50, I would be throwing out those signs, and our numbers would be wrong. So just keep in mind that the 50 degrees does not mean our situation or our math or anything was wrong. It just means I guessed the wrong direction, which is fine, but don't let that mess up your math because you start using a positive. We're going to stick with our negative 50, TLDR. This theta is this theta. They are the same theta. So we can plug this in there and solve for v. So if I just slide this way, we get 0.4532 equals negative 0.7 times the cosine of negative 50 point, what was our 33142 degrees plus v. Now we can just solve this for v using simple algebra. So if I were to just kind of fill this out step by step, 4.04532 equals negative 0.7 times 0.6386, which, according to my calculator, that is the cosine of negative 50 degrees. Plus v. So now subtract negative 0.7 times that from both sides. And I'm just going to multiply this by negative 0.7. Negative 0.447. So I'm going to add 0.447 to both sides, which gives us v equals 0.4532 plus 0.447. I guess for the sake of sig figs, I'll throw a 0 on there. This equals 0.9002 meters per second. And this is our final answer. So this is the second ball, post-colliding, is going strictly in the positive x direction at 0.9 meters per second. And the first ball is going 50 degrees below the horizontal, which means we have solved this problem up here. What was the direction of the first ball? Negative 50 degrees. And the velocity of the second ball? Positive 0.9 meters per second. And this approach that I've done here, this is the approach you do for every totally elastic collision problem. Inelastic is a little different, but not much, and there's going to be another video about that. I hope this helped you some. If you have things you would like me to cover in the future, please leave a comment, and happy learning!